Ashland Henry, Ethan Hawking, Jake Copperstick, Brad Johnny, Levi Gerber, Morgan Grover, Jaden Lake, Farida Malta,
Genetics. Oh,
Roger Nullamickle, Daniel Norris, Reed Stratton, Maya Robinson, Rose Rodman,
the very last.
Michael Rolla, Tyson Roy, Mason Sanchez, John Sears, William Stockton,
Oh, Michael. Really? Let's see. I was pretty check.
Cameron Struck, Benjamin Fisher, George Vogel, Daniel Warner, Jeff Wells, John Wall, Samuel Jackson,
Yes.
Here are the averages for the midterm 3 and your grades as of today. Midterm 3, I was 94. So the average was relatively significantly lower than become 1 and 2. Accordingly, what I did was curve for the total. Usually, last time it was 20%, I did it 25%. So that was basically the balance points that we have lost. Total now, this is total everything, all the points that have been collected as of now. High is 96, average is 80. This is, remember that it's diluted with the homework and quizzes. Probably what has happened with the midterm 3 is that some from here happen to go in here, and this that a little is on an average, if you were to look at it. That's my very superficial interpretation, but not sure about that. I have dropped 1 homework and about 3 quizzes, the lowest 3 quizzes and lowest 1 homework for each of you. And I have noticed that at least between 80 and at least the cutoff for A, there are very few people who are really close to that. So it was very easy for me to serve it so that what can I say, the island or the or that there is no one on the border showed up. What that means probably is that your grades, as far as you keep doing whatever you do, might stay the same. Like I don't see many people jumping the grade unless it can go down. Remember, if you don't work very hard, but still, if what I typically say is that if you have an 87 at this point in your as a grade, it might be possible to make it A, even though 90 is your cutoff. Remember, anything above 89, I round it off to 90. So 87, you have to make it to 89. With the curves that happen, it might be possible. But if it is below 87, meet me if you really want to try on that, and I can give you a more serious distribution of how much you have to get. Remember that for every point you have to increase, you have to earn about 7 points more in the final exam. If you average on an average get 80 and you need to get an 85, if you want to increase your grade to 81, then you have to get 87 in your final exam. That's because it's 15 points worth of an exam, and 15 into 7 is approximately 100. That's the very broad way of looking at it. But since many people do badly on the final exam, statistically speaking, so there are a lot of other factors that come in. But a guideline is that if your score is significantly below 87, it may not be worthy to try for an A. So that's, and the same thing holds for B also. If you're below 2 or 3 points, you shouldn't be trying on it. You should work for the exam, that's different, but don't work for the grade. So that's an advice I have. Anything else? Any other questions about the course as such? There are probably about 20% of the points, so remaining 15% is for the final exam, and homework and other things probably it's 15 or maybe 5 or a little more than that. Okay, so Yep. Homework 9. That's due. There are a total of 3 homeworks remaining, so there are approximately 3 weeks, including this week, in classes, and we have 3 homeworks. We talked about electrostatics, electricity, which is commonly known as electricity. We talked about magnetostatics or magnetism in general. And we also talked about change in magnetic fields creates an electric field, which is what is known as Faraday induction. If you move things around or move a metal around in a magnetic field, it creates a voltage. Another way of saying it is that a change in magnetic field creates an electric field. It was not realized very, even though we had all these equations for about 50 to 70 years, historically speaking, it took some time for one to realize the opposite, that the change in electric field also can create a magnetic field. That's the inverse of the problem. And once you realize that these 2 effects are possible, it turns out that light, as we know it, is nothing but an electromagnetic effect. And it is nothing but a wave, as we see it these days. We often talk about radio waves and gamma rays and X-rays and so on. It turns out that it is exactly a mode in electricity and magnetism. So, in very briefly, since we have limited time, I'll motivate this based on whatever we have studied as of now. So let me very quickly, at least collect the important results that we have, or important laws, you can say. One is Gauss's law. It is a statement of Coulomb's law. Coulomb's law says that if you have a charge, it creates an electric field, and if there is an electric field, it can exert a force on another charge. That can be stated as Gauss's law. What it says is that on a closed surface, break a closed surface into infinitely tiny area elements, still close the surface, and the closed surface is represented as an integral, as a circle on an integral, means it is being integrated on a surface and it is closed. Closed means it occupies a finite volume and there are no holes in that surface. If you do the integral of the electric field everywhere on that surface, take any arbitrary closed surface, and if you were to calculate the component of the electric field perpendicular to the surface at every infinitely tiny element of the surface, it turns out remarkably that it will give you the total charge inside the surface. So this means inside, or is that what we used? Enclosed, right? We actually said enclosed. That is the reason. Use the word enclosed here. enclosed. Enclosed means enclosed in the surface. This circle around the integral means that there is a closed surface, and whatever charge is there inside that surface. So this could represent that surface. So S here, and that is closed. It's a three-dimensional surface, and that's a representation of the three-dimensional feature of that. It doesn't care for what are the charges outside the surface. It only cares for the charges inside that surface, and the electric property of vacuum, that's the permittivity of vacuum. This is a statement of Coulomb's law, and we have used how to use this as part of our first couple of chapters in this semester. There is a similar expression for the magnetic field. You can say Gauss's law for magnetic field, but there is no name given for this law, and this is a statement, the same statement for magnetic field. Again, pick any arbitrary surface and you calculate the magnetic field components perpendicular to the surface, break the surface into many elements, find the component of the magnetic field at every element, and what is this going to be equal to? This should equal the source of magnetic field. Here, electric field is created by charges. Positive charge creates an electric field, and the electric field ends on a negative charge. So this is a source of electric field. Magnetic field has a source in the form of a north pole, but north poles are never isolated. They always come with the south pole. So in principle, there is no source for magnetic field, and due to that reason, this is equal to 0. The magnetic field is very special in the sense that we never see magnetic field coming out of a point. Remember, electric field always starts from a positive charge and ends in a negative charge. So it originates from a positive charge, ends in a negative charge. Magnetic field is not like that. You'll never see it coming out. Yeah, it in principle comes out of a north pole, but north pole doesn't exist on its own. North pole always comes with a south pole. So in that sense, magnetic fields are always circles. Since there is no north pole or south pole, magnetic field will always be in circles. There will never be an origin for magnetic field, even though often we represent it as if there is a north pole, but in principle there is no north pole. The solenoid is a classic example. That's a solenoid. The magnetic field is like that. And it goes through and then comes out. Right? It's in circles. You never have an initial origin of the magnetic field and an end to the magnetic field. These two statements, that electric field has sources, which are actually charges, and magnetic field do not have any static sources. The only way it can be produced is by moving a charge, and that statement is given by, you can say it is the Gauss's law for magnetic field. This is the Gauss's law for electric field. Since we do not have a name associated with that, we can say it is the Gauss's law for magnetic field. We next saw Faraday's law, or before that we saw Ampere's. Ampere's law was not for surfaces, so this is for a surface, but this time this was for a loop. You write this is a surface. That's a surface. And this one is for a loop, and you create a loop integral, which means you create a closed loop with a curve. It has any straight line, any curve coming back to itself, make a loop out of it or a circuit out of it, And if you were to calculate the magnetic field that is tangential to every point on the loop, break that loop into infinitely tiny elements. Each element has a tangential element to that, and find the component of the magnetic field along that tangent, and that will be equal to the current that's going through the loop. So this is enclosed again. So this time we have pick any loop again. So this is a curve or a loop, and calculate the magnetic field everywhere tangent to this. So the magnetic field could be here. Calculate the component tangent to that, and it will always pick the current that is coming out or going through it. So this could be I1, that could be I2, that could be I3, and it will add up all these currents, I1 plus I2 plus I3, and that's what it will be equal to. It is a statement that magnetic field is given in terms of the current, or magnetic field is produced using current. And we have Faraday's law. So these are the four Faraday's law of induction, and here we said we wrote it as a voltage. Induced voltage is equal to change in flux, but this cannot voltage is nothing but a line integral of the electric field. This is the work done per unit charge, right? Work done by the electric force per unit charge. So that's E dot into dl. That's a voltage. Electric potential energy, which is the work done by the electric force, is equal to the, you take any path and you find out how much work is done by the electric force, which is electric field times the charge. And that's equal to the negative rate of change of magnetic flux. And flux itself is equal to B dotted with the A, but this time not on a closed surface. This is on an open surface. Flux is defined on an open surface, and if you were to calculate the flux in a closed surface, then that's equal to the source. That's your four laws we have spent significant amount of time during the semester. And this was the status in about 1820, when the actual, you can say, technology or technological revolution was happening. And it was realized by Maxwell that there is an inconsistency in this. There is a mistake in this. And the inconsistency is the following. He did the following setup. And it should be appreciated that these laws were known by 1810, 1820s, and it took all the way till 1860s to 1865 to realize that there is some inconsistency in this equation. So it's a subtle inconsistency, and here is how you can motivate that. Consider an RC circuit. So we have a battery, we have a resistor, and we connect it to a capacitor. And I'm going to throw the capacitor in slightly enlarged form because I want to put some details in there. So that's a capacitor, that's the resistor, and we have described what happens here. This is a voltage, that's a battery, that's a source of positive and negative charges. And if you connect this, if you were to put the switch on here, on the positive charge, start coming here and collecting. This happens in not instantly, but it happens in a certain amount of time. And if you were to plot this, if you were to plot the charge that is collecting on the surface of the capacitor, on the capacitor plate, it reaches a saturated value, but it takes forever to do that. But it very quickly reaches about 90 to 99% almost in a microsecond or so, but it never really reaches the saturated value because it takes infinite amount of time. It's only asymptotes to that value, but it very quickly collects that, and this is V over R. VC, right? 2 over 3 is C, so it's V times C. That's all, yeah. I think so. The amount of charge it will collect is that. I think so. Yeah. If I remember correctly, that's the amount of charge it will collect, and that is a time constant tau here, which is R3. But the main point is that there is a current that is going through this wire while it is getting charged. And let's think of that particular current here. So there is a current that starts from here and it goes all the way till here. There is no current in between the capacitor. There is only a current in the wire that is there before the capacitor. And now let's think of Ampere's law. Ampere's law tells us that any loop, you can imagine any loop. This is an abstract loop. This is not really a wire. Think of any loop, and Ampere's law will give you the current that goes through it. And now let's see an inconsistency in here. This is what Maxwell suggested. Let's think of the loop to be the following. This is the loop. So that's your Ampere loop. That's what I'm Ampere loop. And if Ampere is correct here, it should tell us, if we calculate all the magnetic field on this loop, that is tangential component of the magnetic field tangent to that loop, it should actually give us the amount of current that is going through it. And the amount of current is described by this curve. That's the charge rate at which this is growing. That gives you a current. And it seems to be okay that there is a magnetic field. We know that there is a current carrying wire. There will be a magnetic field, and that will be associated with this current. So everything seems to be okay. But this is a curve, and the point is, how do we know that this is actually passing through this loop? For that purpose, we have to talk about a surface that is bounded by this curve. So to find out whether there is a current going through this loop, you will talk about a surface that is bounded by this loop. And then it turns out that the surface that is bounded by a loop is not unique. For example, this loop bounds the following surface. That's a surface, just a flat surface. And this curve bounds that surface. And that surface is having a current going through that. That is a current that is penetrating to the surface, and you would say that, of course, we have an iron curve. But Maxwell said that that's not unique. There is another curve, and here is another curve. This is now like a hat. And that's also a surface. So think of a cup now, which is enclosing one of the plates. And again, we ask, there is how much current that is penetrating through this surface. And you will realize that there is no current penetrating through the surface. The same curve can be thought of as bounding more than one surface. The surface is not unique, so there is an arbitrariness in that, and that should be okay. You should be allowed to have any surface that is bounded by that curve, but then the answer should be unique. The answer doesn't seem to be unique. If you take this surface, there is a current I going through this. If there is this surface, that doesn't seem to be an I going through this. So if you were to evaluate Ampere's law using these two surfaces, so let me call that S1 and this is S2. So DL dotted with B on this curve, that's your curve, will be equal to mu naught times I. That's passing through this wire for surface 1. And it will be equal to 0 for surface 2. And you would say that's not consistent. It depends on the surface that I'm using. So the answer is not unique, but physics does not care for what the person is doing, what the observer is doing. It should be unique. So that is an inconsistency. And for that purpose, Maxwell said there must be a contribution to the right-hand side on S2 also. And for that purpose, he said this must be the electric field here that is contributing to that. Exactly like magnetic field, change in magnetic fields creates an electric field. He suggested that the change in electric field here, because the charges are increasing as time evolves, the electric field changes. The change in electric field is what contributes to the left-hand side in here. So this is not complete. There is a new term in here, and that's equal to time derivative of the flux of the electric field this time. This was a flux with the magnetic field, but there is a flux for the electric field. And there is a lot of symmetry in here, except for the charges, where we have sources for electric field, but no sources for the magnetic field. That has been taken into account. There seems to be all the rest of the symmetry is still there. That is a change in electric field creates magnetic field, change in magnetic field creates an electric field. For dimensional purposes, we need to add some more quantity. This is not dimensionally the same as this, so we need an mu naught and an epsilon naught. That's just for dimensional purposes. When you take care of your units properly, then this comes in. This is the Maxwell displacement current. So this acts like a current. From here to there, there is an actual physical current going. But between the capacitor, Maxwell interpreted that there is a current, but it is only an effective current in the form of electric field. The change in electric field is contributing to the current, and then there is the actual current that flows from the other side. So this is called the displacement current, Maxwell's displacement current. And this was suggested in 1862, somewhere around 1862. Those papers span a time of 1860 to 1865, but that was a very significant, or the implication of this term is very significant, because now what you're saying is that electric field can create magnetic fields, magnetic field can create electric field. You do not need any charges in between. You can get rid of these charges And an electric field, a change in electric field can sustain a magnetic field, and a change in magnetic field can in turn sustain an electric field. And that configuration is what is light. Light does not need any charges. Light does not need any current. The change in electric and magnetic field can sustain each other. So that configuration is what is light, and that leads to the whole field of optics. And let's write that down. Let's write those equations down separately. Remove the current, remove the charges, and we have only the electric field and magnetic field supporting each other. So what we have is magnetic field is equal to mu naught times epsilon naught times the rate of change of electric field and the inverse, right, or the opposite if you want. The L dotted with E is equal to minus of d by dt of the flux and the flux of the magnetic field. Again, the significant feature in here is that even without a charge, without a current, which is necessary for all the configuration that we have been studying till now, that's not needed. Remove the charge, remove the current, still we can have a configuration of electric and magnetic field. Electric field will sustain the magnetic field, a change in electric field, and the change in magnetic field will sustain the electric field. So they will sustain each other, and that's called an electromagnetic wave. This combination is called an electromagnetic wave. This is written in an integral form. So let me write this equation in a differential form. So this is a wave equation. A differential equation for a wave equation, and it is equal to the second derivative with respect to x. I'm writing this for one dimension. In general, this is a three-dimensional quantity. An electromagnetic wave can move in all three dimensions. This is wave equation in one dimension. One. Electric field is equal to mu naught times epsilon naught times the time derivative of the electric field, and the same thing for the magnetic field. In fact, this equation, if you ever see an equation of this kind, this is called a partial differential equation describing a wave. When you see an ocean wave, it is described by the same equation, except that the interpretation will be different. That it is the amplitude of water, how or the surface wave of ocean is described by how high is the water from its equilibrium position. This quantity here, let's say any function f is equal to 1 over velocity squared. So that's a wave equation, and we is the velocity of the wave. So that seems to suggest that if you have such a disturbance of electric and magnetic field where one sustains the other and it can be in equilibrium without it getting decayed away, we have a velocity of such a mode given by epsilon naught and mu naught. When we compare this, we have 1 over mu naught times epsilon naught, and we take a square root of that. That's the speed or the velocity of this electromagnetic wave. But we give a special name for this. It is the speed of light in vacuum. It is important that we say it is the speed of light in vacuum, because in that sense, to our knowledge, there is nothing that can go faster than that speed. But that doesn't mean that light always goes with the speed. If you're in a medium, light can go slower. In fact, it does go slower a little bit. It's a factor of 3 or 4, or it can even be larger in a very special material. But in glass and typical materials, light goes slower by a factor of 1/3 or sometimes 1/5 and so on. When it is going slower, that also leaves you with the idea that something else could be going faster than speed of light in the medium. When we say that nothing can go faster than speed of light, we mean the speed of light in vacuum. But if light can go slower than speed of light in vacuum, so there is some room there, something else can come and go faster than the speed of light in the medium. And in those situations, you see effects like shock wave. Shock wave is a feature that you see for sound waves. Whenever a fighter jet goes around you, you often hear a wave that is pretty much having a lot of energy in it. It often you can feel that wave. And that's what is called a shock wave. It actually can break glasses. There is a lot of energy in it. Look it up. What that means is that things can go faster than speed of light in that particular medium, and that is called Cherenkov effect. But that's just a popular point I wanted to mention. Here, what we want to point out is that this is speed of light in vacuum, and that's the constant that we have. And it turns out that this is about 3 × 10⁸ meters per second. But now we have set other constants. Remember, these are measured quantities, and we have some liberty of how much we select it to be. So we select this number to be a perfect integer since 2005. So that's 299,792,458 meters per second. For our purposes, if you are working in 2 significant digits, that's nothing but 2 significant digits. It's 3.0 into 10⁸ meters per second. That's a very large speed. In fact, that's the fastest speed we can have. Notice again that in 1862, it was realized that magnetic field and electric field can sustain each other. That means there is such a wave possible. Before 1862, there was no thought of a radio wave. We never had a radio wave before that. But the moment this equation was written down, it was very clear to everyone that we can actually have a wave of electric and magnetic field, exactly like an ocean wave, which can be used for communication. And within 10 years, in a lab setup, which means in a room, you could actually communicate from one corner of the room to the other corner you could send a pulse and it could be detected on the other side. And then it was just a matter of making it better and better. And you could very soon, within almost 10 years or so, by 1885, also you could go, you could take a signal across the Atlantic. Earlier, there were telephones, but they used to go through wires underneath the Atlantic Ocean. And there was a lot of technology associated with that, where we used to have cables going through it, and this electrical wire used to carry the signals there. And those were, so we had telephones there. But now, after 1885, we could use radio waves to do the same thing. So no wires necessary. You could actually communicate through radio. And this also leads to the idea that this is the speed. And when we are talking about a wave, what sort of wave is this? So let's have a more detailed feature of this wave. So this is an electromagnetic wave. Think of one direction, exactly like you imagine an ocean wave. How do you see an ocean wave? You have, let's say, a reference line here, and there is some physical quantity that is changing or oscillating in both time and position. So what is happening in an ocean wave is, this is first presented to be an ocean wave. That's an oscillation. Now this is X. But if you notice, this is a snapshot of an ocean wave. This is not how an ocean wave looks like. When it is in real motion, it will actually oscillate like this point. So this is a snapshot at time t. So you take a picture of ocean at a certain time, it will look like this. And if you were to click the same picture an instant afterwards, this will go down here. And it will go down and come back. So there is an oscillation in time, and there is an oscillation in space. That's what a wave is. A wave means there is an oscillation in both position and time. And it happens in such a way that a particle, so you think of an ocean, there is a small object right on the surface of the ocean. When in a real ocean wave, this particle will go up and down. If there is a water particle in here, that is actually going up and down. But if you were to stand here, you can feel the pressure of the ocean wave. It can actually push you, and even it can slap you in the sense that there is a significant amount of energy in the transverse direction, even though it is actually oscillating in the, or I should say, that's the transverse direction, the perpendicular direction. You can actually have a lot of energy and momentum that is transmitted in the horizontal direction. So that's what a property of a wave is. Oscillations in space and time leads to a propagation of energy and momentum in a certain direction. So let's pick up some properties of this, so that whenever I draw such a curve, it is understood that this is only a snapshot and it is actually oscillating in time. I cannot show the oscillation in time at the same time when I'm showing the oscillation in space. This is the oscillation in electric field. This could be the not so high, it could be the same value in here, and that's electric field now. Instead of an ocean wave, now we are talking about an electromagnetic wave. These are electric fields. Electric field, no charge noted. Every time we were talking about the electric field, we said we need a charge to create an electric field. But now it is the magnetic field that is creating the electric field. No charges, no current. The electric field oscillates. That's your electric field, and it keeps oscillating as you move on to the x direction, and at a certain amount of time, this is what it is, but at the next moment, it will keep oscillating and you will have up and down changes in electric field. What about the magnetic field? How is this sustaining itself? It is the magnetic field that is sustaining, and it is perpendicular to the electric field. So this is perpendicular to that. And the magnetic field is also, and it can be shown this way. This is in a perpendicular plane. So that's perpendicular. And you can show that by now this is magnetic field. This is magnetic field. This is parallel to that. And it oscillates. And hopefully that is clear. So that's your electric field. Electric field and magnetic field as there horizontal. Hopefully that's clear. A different color will help, but that's all. So there are two ways, which is changing the physical quantity as time goes, but the change in electric field, the change in time, right? Change in time in the electric field creates a magnetic field, and the change in magnetic field creates an electric field. So it's able to sustain by changes in each other, a very non-trivial phenomena. We are talking about electric and magnetic field independent of charges and current. Once we have oscillations in space and time, that means we can create or we can associate variables describing those oscillations. Whenever we have an oscillation, we are talking about repetitions. Something is happening again and again and again and again. That means it's periodic. Anything that is periodic has a time period associated with it. So periodic in the oscillation in time is called T, and that's time period. That is oscillation in space. That also has a periodicity, and that's called a wavelength. In this diagram, this is the space that we are talking about. Oscillation in space will be periodicity in space. So from this point to this point, that's the periodicity, that's wavelength, that's lambda. And there is a time period also. Where is the time period? You start from this point, and I said if you were to remove this time constraint, this will go down and come up, down, up, and so on. The amount of time it takes to start from the top, go down, and then come back, or for that matter, start from anywhere, and it retraces its path. One cycle in time is what is time period. So any wave, even an ocean wave, has a time period associated with it, and it has a wavelength associated with it. When you have a time period, you have a very associated terminology for the frequency. Sometimes you say a bus comes to a bus stop once in 20 minutes, or you can have the frequency of the bus is 3 times in 1 hour. Same information. Whether you talk about time period or frequency, it is the same information that is going in. One is talking about what's the information about one cycle, and the other is talking about in a certain unit of time, there are how many cycles, the same information. So once you have a time period, you talk about frequency. So a time period has an associated terminology called frequency, which is nu, and that's nothing but 1 over time period. If you know the time period, you know the frequency. That one and the same. It's just a reciprocal of the other. Question? New. So I think it's new. That's how it's pronounced. Greek letter new. So that's new, and that's 1 over time period. Sometimes we talk about angular frequency, and omega is 2 pi nu. All of these are the same concept. If there is an oscillation in something, you associate a time period to that, then you can talk about a frequency and you can talk about an angular frequency. This is an oscillation in space. There is a lambda associated with that. You would say 1 over lambda. And what is that? There is no terminology for that. Instead, here, instead, you say this is 2 pi over lambda is k. What is 1 over wavelength? Anyone? 1. I think there is nothing, that's a standard definition at least. One would have thought that it is the same associated definition. Never realized that. Okay. I think there is none, but instead we say this is wave number. So this is wave number. So that's frequency, angular frequency, that's wave number. But for our purposes, there is a lambda and a time period, and often we will use the terminology of frequency in them. In a wave, these two are connected. If you have a wave, we talk about how much energy is being transferred to the along the horizontal direction, and that's called the direction of propagation. So this now, even though we said it is x, this is also now the direction of propagation. And you say, what is propagating in that direction? And every particle is actually going vertically up and down. What exactly is going from left to the right? That is energy being transferred, energy and momentum associated with the wave is propagating in the x direction, and that's the direction of propagation. And that particular propagation has a velocity, and that velocity will be given as lambda over time period, always for any wave, which is also 1 over t is frequency, lambda times frequency. That's true for any wave, but an electromagnetic wave is very special. Its speed in vacuum is a constant. It is 3 × 10⁸ meters per second. That means that these two are not independent. Even though here in an ocean wave, for example, the wavelength and time period are not constrained at all. The velocity could be dependent on what kind of water. If it is a viscous liquid there, then you have a different velocity, and if it was a non-viscous liquid in that region, then velocity changes from place to place, but not for the case of electromagnetic wave. As far as it is in vacuum, it is always the same speed, and if it's the same speed, then the wavelength and frequency are related for an electromagnetic wave, and that's equal to speed is equal to lambda times nu. So speed is a constant. This is 1 over epsilon naught over mu naught. That means to say that wavelength and frequency, the oscillations in time and oscillations in space are not independent of each other in an electromagnetic wave. They are connected. They are the same, one and the same. It is just a matter of using the speed of light to convert one to the other. It is good to know what is actually the frequency associated with electromagnetic wave. It can be anything. It can be very small to very large. But the most important electromagnetic wave we have around us is light itself, visible light. And for visible light, the frequency is, for visible light, the frequency is about 10 raised to 15 hertz. That's very large. So I could say that's frequency, right? So that's mu. And wavelength is about 700 nanometers, which is about a micrometer, right? So let me say this 600 nanometer. It goes anywhere between 400 to 700 nanometer. 400 is blue light, 700 is red light, and anywhere in between is your visible light. And the oscillations, number of oscillations that electric field, when you think of an ocean wave, the surface wave is oscillating. Same thing here, electric field is oscillating. How many times does it oscillate per second? 10 raised to 15, significantly large. So if you were to shine an electromagnetic wave on a metallic sheet, it is actually oscillating an electron 10 raised to 15 times per second. That's significantly large, and the electrons really oscillate based on that frequency. Let's also talk about energy. I said that a wave propagates energy and momentum, so it's good to know how much is the energy that is contained in a volume of space. The energy density, so energy per unit volume is equal to, some of it is in the form of electric field, so that's half epsilon E squared, and some of it is in the form of magnetic field. So that's the amount of energy per unit volume. When you think of light, the light that we see around us, there is an energy per unit volume of space. Think of any small cubic centimeter cube of space, and there is this much amount of energy in the electric field, this much amount of energy in the magnetic field. In fact, these two are exactly the same. The amount of energy in electric field is exactly the same as the amount of energy in the magnetic field. So some properties of an electromagnetic is in order. So let's say, first of all, electric field magnitude is equal to C times the magnetic field. That's in there. That's one property. Second is our lambda times nu is equal to C. That's energy density. And third is the direction of propagation is always equal to E cross B. E cross B, if you take the cross product with your right hand group, point your fingers in the direction of electric field, keep your palm in the direction of B, and the thumb gives you the direction of the cross product. So along the x direction, that's the direction of propagation. So that's equal to K over omega times U. So that's the energy density that is coming in. And K is K times K hat, where this is direction of propagation. Once you have this bunch of properties, it is very nice to observe that there is a whole energy electromagnetic spectrum available for wave propagation. And very quickly, in the last 8 minutes, let me try to point out some of the nice features of that. So we already said that the oscillation in space, oscillation in time, they are not independent of each other. They are constrained by the speed of light. So one parameter is sufficient, and let's choose the wavelength to be that parameter. If that wavelength is about a micrometer, that's 10⁻⁻⁶ meters. That's the size of a bacteria. A bacteria is usually of the size of a micrometer. That's visible light. So that's visible light. It's more accurately 400 nanometer to 700 nanometer. And it turns out that is a general principle that if you want to see something of a certain size, like a bacteria is 10⁻⁶ meters, then you need an electromagnetic wave of that wavelength. At least that much of wavelength is needed. So, for example, a visible light can be used to see a bacteria, but you cannot use visible light to see wires because wires are significantly smaller. They are only nanometers. So that's a nanometer. So that's 10⁻⁹ meters. That's the size of a wire. And then you cannot use visible light. Instead, you will need to use X-ray. So that's X-ray. If you even go smaller, somewhere here is about 10⁻⁻15 meters. That's the size of a nucleus. This is approximately the size of an atom. 10⁻⁻10 meters is the size of an atom. A nucleus is a proton is 10⁻⁻15 meters. Then you need a gamma, very high energy. Gamma. So that's energy. Energy increases in this direction. That's the wavelength. The periodicity in space, the energy increases on this side. We are not used to exposing ourselves to X-ray and gamma rays, and we are mostly protected by our atmosphere. Our atmosphere is practically opaque to gamma rays and X-ray. And that is why if you have to use a X-ray for astronomy purposes as a telescope, and you have to go out of space because atmosphere is completely opaque, it doesn't pass on any signals. It's opaque to gamma rays, it is opaque to X-ray. But it is actually transparent to radio waves. Radio waves is somewhere, let's go 1 hour first here this side. That's 10⁻⁻3 meters. That's a millimeter. A millimeter is approximately around this to 1, right? This is about 10⁻�0. That's 1 meter. This is a microwave. So this region is what is broadly called a microwave. The microwave that you see in that you use for cooking, that has a wavelength of 6 centimeters. All the microwaves are designed in such a way that the wavelength is 6 centimeters. You can test this. Usually you have a small plate that is rotating inside the microwave. Remove that and keep a loaf of bread or anything that is static inside, and do not heat it too much, or that doesn't conduct heat very easily. You will see that two places that are hot enough, they will be separated by 6 centimeters. That's because the electromagnetic wave that is oscillating more, this will be hotter, less hot here, because this is not oscillating. A microwave practically is designed to oscillate water molecules. The only thing that a microwave does is wherever it sees the water molecule, it will start oscillating. And that oscillation is what we see as heat. So if you have a material that has no water, it will be microwave proof, and you won't be able to. So we are not microwave proof at all. If you put a microwave on us, we have a lot of water, it will burn us. In fact, it will burn us from inside. It can penetrate the body. It is not just a surface that it is, it can actually penetrate inside. So that's a microwave. Take it further out, that's 10⁻³ meters, and that's what is called a radio wave. And remarkably, our atmosphere is actually transparent to radio waves, which means that you can use that to see things outside the face. If you want to look at stars in the radio regime, we typically use visible light. Our atmosphere is transparent to visible light, but it is very nicely transparent for radio waves. So we use that for radio astronomy, and that is how gravitational waves were observed. That primarily used radio waves. You can go further out, and what is that? I don't know that. Anyone else? I don't know. Beyond that. Okay, so I will stop with that. I have 2 more minutes. A lot of interesting things you can say about that, but I'll stop. Thank you.